So I now understand the B58, CSE B58, I think, as another review seminar at the same time. Um, to be honest, I'm not sure where Kevin is. I know he did pre-record his part, so I'm not sure if he's coming here or not, but that's all right. Uh, we'll we'll both post the recordings for this review seminar after it's finished, so it might end earlier than 5. Um, so it'll be similar to the midterm review seminar. I don't know how many people went to that one, but I'll just be going over questions and then just briefly touch on content that you'll need to know for the final. So I'll be covering these three. Kevin was supposed to cover these three. I don't know if he's coming. I did see he has a recording up, so I'll make sure to post that as well if he doesn't show up. So anyways, we'll get started. So the first question on your final is likely going to be two population comparison. Um, you will have a formula sheet, but the only thing that you're given is just the equation itself. So you won't be told which scenario that you would use essentially. So like on your formula sheet, it wouldn't say like equality of two variances. Like it would just say this, and you'd have to, based on the problem, you have to apply the correct formula. So make sure for each of these sort of tests, you know when to apply it, and also um, like the appropriate scenario. So like obviously there's only one for equality of two variances. So if you ask you that, then it's just this one equation. The two means ones you kind of have to know. If you know the variances, then it's this very simple one, this very simple test statistic that follows a normal distribution. And if you don't know your variances, then it follows a t-distribution. And then if you have unknown equal variances, you have to do just the pooled one. If they're unknown and unequal, then you have to calculate this crazy degrees of freedom calculation here. So just make sure you know all four and then when to apply all four. So I'll give you 2 minutes to do this problem. In a study, suppose you want to test two types of energy drinks and study the amount of hours students are able to focus on the task late into the night. We took 14 students for each energy drink, 28 total, and then we have the summary statistics below, and it's asking you to do the test and make a conclusion. So I'll give you 2 minutes to fill this one. Oh yeah, I'll post the slides and also post the recording as well. All right, so maybe not enough time for this problem, but I'll go over it now. So it's asking you to test the equality of variances. So this one, you should be using this formula here. So again, we want to test the null hypothesis that the population level variance for X is the same as population variance level for Y. So in our test stat, or under the null hypothesis, we have that sigma squared X is equal to sigma squared Y. So these two just cancel out. Oh, sorry. These two will cancel out, and then your test stat is just S squared X over S squared Y. So I gave you guys the sample standard deviations here. So you're just plugging in values. So it's just 2.47 squared divided by 1.94 squared. And again, you just put into your calculator, you'll get 1.621. And it follows an F distribution with these degrees of freedom. So again, we had 14 for both X and Y. So this will follow an F distribution with 13 degrees of freedom for both. So now that we have our test statistic, we need to get our rejection region. So in our rejection region, it is a two-sided test. So it's from negative infinity, F alpha over 2, n minus 1, n minus 1, and then F 1 minus alpha over 2, and again, n minus 1, n minus 1 to infinity. So I'm not sure if he gives you guys the rejection region for each one. If you might just have to memorize this. But yeah, all it's saying is like on the F distribution, I think it looks something like this. It's very heavy on the left, on the like the right tail. It's a sort of a right skewed distribution. Uh, you're just finding the value to where it's basically here and then here, where this is like, let's say around 2.5%. This area is 2.5%, and it's just 5%. And it's just basically if your statistic lands within the region, then you'll reject the null hypothesis. So he'll give you guys a table value in the back of your formula sheet. So so here, let's just say, did I give an alpha? Oh, I did, 0.1. Okay, so if it's 0.1, then this will be 0.05, 13, 13, and then F is 0.95, 13, 13. So pretend this is an F distribution with 13 degrees of freedom. Then what we're doing essentially is we're just taking off 5% on both sides here. This area is 5%. And then basically if it lands in either of these regions, then we'll reject. So the value for this is 0.388 and then 2.577. So if you can imagine, this would be 0.388, 2.577, like this value there, right there. So then our conclusion will be, since our test statistic doesn't fall into our rejection region, we fail to reject the null hypothesis, sigma squared X equal to sigma squared Y at alpha equal to 0.1. Any questions for this two population comparison problem? If not, we'll move on. So the second problem now is asking for just focus on part one is the main part. These are kind of just follow-ups. Now we want to test that the data provides evidence that the average focus time between the two groups are different. Let's assume the population variances are unequal. Test H naught mu X equal to mu Y versus the alternative what's not equal at alpha equal to 0.1. I'll give another 2 minutes to do this one and then I'll go over it. All right, I'll go over this now. So now we're trying to do an test for the equality of the means. So we need to choose the correct formula out of the three. So in the problem, it said we have variances are unequal. It actually didn't say anything about if it's known or not, but well, if it's unequal, did I mention something? Let's assume they're unknown. Yeah, I should have fixed that. That's my fault. All right, so if they're unknown, then the first thing we need to do is calculate we need to do the degrees of freedom calculation. So this is V here. So again, I'll just put one here. So V is S squared X over N plus S squared Y over M all squared divided by S squared X over N squared over N minus 1 plus S squared Y over M all squared over M minus 1. So then this is you're just plugging in numbers. So 2.47 squared over 14 plus 1.94 squared over 14 all squared. Oops. So yeah, you just put this like big equation into your calculator. You'll get around 24.62. And since it's a degrees of freedom calculation, you'll need to round to the nearest whole number. So let's just say this is 25. Okay, so now that we got the degrees of freedom, we need to do the test statistic now. So mu x equal to mu y. This is the same thing as testing mu x minus mu y is equal to 0. So in our test stat, we need to calculate this. So it'll be x bar minus y bar minus mu x minus mu y divided by the square root of s squared x over n plus s squared y over m. Now, since under the null hypothesis, this equation or this is equal to 0. This is just going to be 0. So you'll get sorry, x bar minus y bar over the square root of s squared x over n plus s squared y over m. So after that, now you're just plugging in values. So I think x bar is given here. Oh, maybe, sorry. Yeah, I should have scrolled up. That's my bad. But yeah, 5.64, 7.38. Yeah. Yeah, if you know which test statistic to use, and then you have just a formula written down. It's just about plugging in values. I would say you probably got the answer correct. You'll probably get the answer correct as long as you just put it into your calculator correctly. So again, now it's just about plugging in the numbers and putting things into your calculator properly, and then you'll get negative 2.073. So then now we need the rejection region. So the rejection region. So since this follows a t distribution with 25 degrees of freedom, I'll just write it down, that we calculated earlier up here, we can now figure out the rejection region. So the rejection region is from negative infinity to t alpha by 2 with 25 degrees of freedom union t1 minus alpha over 2 degrees of freedom equals 25 to infinity. So again, you'll be given the table values. So this is negative 1.708 union 1.70. Oh, actually, you know what? I'll write it down. Okay. So that's, sorry, this is t, what's alpha here? 0.1. So 0.05 t 0.95. And now you just look for the table value. So there's your rejection region. And then so your conclusion would be, since the test stat falls into our rejection region, we reject the null hypothesis at alpha equal to 0.5. We conclude that mu x is not equal to mu y. If he asks for R code, I'll go over that too. So essentially the rejection region is just, like, imagine this is a t distribution with 25 degrees of freedom. So what we get here essentially is here, this area here is 5%, and this area here is 5%, which gives us our alpha equal to 0.1. And then this would be negative 1.708. So if he asks you to get the critical value, like these values here, then you would do the quanta, so qt, and then here you would specify the probability and then degrees of freedom. So I'll write it out so it's clear. So here qt 0.05, and then degrees of freedom equal to 25. So in R, whenever you do quantile, it'll give you like the quantile values on the distribution. But you have to remember, in R, it's always going to do the lower bound tail, if that makes sense. Like it'll always be like, let's say I want to find this quantile here, it'll always be calculating to the left of that, like the probability to the left of that. So if I did qt 0.95, oh wait, this is for probability. My bad. Yeah, so if you do 0.05, it'll give you sort of the left side where 5% of the distribution is covered. And then if you do 95, this is where sort of 95% of the distribution is covered. And that's 1.708. Now, if he asks for R code to get the p value for this, and then make a conclusion, you would do you'll do PT. So PT will give you the probability at a specific quantile. So if you just put in PT negative 2.073 degrees of freedom equals 25. Yeah. And what that'll give you is it'll give you sort of this area here. But usually you'll be asked to just form the rejection region, I believe, and then make a conclusion. Anyways, any questions for part one? So part two is asking, how would you do it if the population variances were equal? Okay, so again, if the population variances were equal, then you would be using this formula here, formula 3. So then you would be calculating this S squared P here. So it's the same. Oh, it's not the same. So it's sort of the same approach. You would calculate this first, and then you would calculate this, get a t-value, make a conclusion. So that's the approach for part two. So I guess I'll just write it here. This is your test statistic now. And then you calculate SP. Part three. So if you're asked to do a one-sided test with your alternative is either mu x less mu y or let's say mu x greater than mu y, then you need to formulate your rejection region slightly differently. So let's say your alternative was mu x less than mu y, then your rejection region will be from negative infinity to just T alpha and then the degrees of freedom to whatever the degrees of freedom you calculated. Similarly, if you wanted to test if it's greater, your rejection region is from T just 1 minus alpha, and then degrees of freedom is whatever you calculate. Oh, and to infinity, sorry. So what this will look like is your sort of rejection region will be, imagine this is a T distribution with some degrees of freedom. And then this area here, let's say we kept the same alpha equal to 0.1. It'll be essentially like whatever this is T alpha value, and then this will be 10% here. And then another case, let's say this is T as well. Then the 1 minus alpha will cover basically this area. Hopefully that makes sense. That's the one-sided. Oh, and sorry, this is the area equal to 0.1. So how would you test? Also, part 4, how would you test mu x equal to mu y minus 3? So if he asks you something like this, then it's just a matter of moving stuff around. So mu x equal to mu y minus 3, then your thing will become mu x minus mu y equal to negative 3. And then you would plug that negative 3 into this here. Or whichever one, if you use like this one here. So hopefully that makes sense. Any questions for the practice problem 2? Here's the full answer if anyone wants to take a screenshot. If not, moving on. So now, okay, so those were the two population like practice problems I had prepared. Now is going to be on like sufficient statistic, large sample stuff. So I'll start with, so I'll just quickly go over some background for this. So these were prepared by a previous, what do you call it, like the person that also ran the review seminar. So just if he asks you to find a sufficient statistic, you just need to be using the factorization theorem. And essentially what you just need to do is you need to separate your likelihood into two parts, one with just the observations and one with the observations and sort of the parameter that you're trying to like sort of maximize here. So, and then this value is considered your sufficient statistic by the factorization theorem. So if you didn't understand what I mentioned, I don't know, I didn't give a good explanation, but I think it'll be clear once I go over the practice problem down here. And then the score function is just, I think many of you guys already know after the midterm, it's just the first derivative of the log likelihood. And then this property here, the expectation of the score equal to 0, this is usually a property he might ask you to prove on the final or show on the final. Anything else? That's enough. So For this problem here, would you guys like me to go over it now immediately, or do you want me to give you some time to try it? It's up to you guys. All right, now I'll give everyone 2 minutes to try it. All right, so I think maybe not enough time, but I'll just go through it now. So we need to get the likelihood. Take the first derivative of the log likelihood, or take the log likelihood and the first derivative to get the score, and then show that the expectation of the score goes to 0. So we'll start off with the likelihood. So likelihood, I'll try to make this as explicit as possible. So it'll be e to the from the PDF here. It'll be e to the sorry, not e, x1 over beta e to the negative x1 squared over beta, 2 beta, 2 beta, 2 beta times x2 over beta e to the negative x2 squared over 2 beta. And then we have n of these, so xn over beta e to the negative xn squared over 2 beta. So if you just want to write the product, it will just be this xi, oops, times 1 over beta to the n exponential of negative 1 over 2 beta sum of xi squared. Again, it's just combining these terms together. So we'll just have a product of xi's here. The betas are all constant, so it'll be beta to the n. And then at the end, we're just taking the product of a bunch of exponentials here. So this will become the sum. Hopefully this is nothing new to you guys. You guys have to do this on the midterm. So then we take the log likelihood. So log the product of xi's minus n log beta minus 1 over 2 beta sum of xi squared. So then taking the first derivative, so this will be 0. Also, actually, we're taking the derivative with respect to beta, so that'll go to 0. The derivative of this is n over beta. And then this will be 1 over 2 beta squared sum of xi squared. And then, so this is the score function. So this is equal to the score. So we need to take now the expectation over this. So it'll be negative n over beta naught. Sorry, I should specify this here. So this will beta naught here. Yeah. Plus 1 over 2. Oops. 1 over 2 beta naught squared. Expectation of the sum of xi squared. So this will be we're just applying expectation inside, so it'll be the sum of each of the xi squareds. And then we're given the expectation here of the second moment is 2 beta naught. So we'll just use that. So 1 over 2 beta naught squared times n times 2 beta naught. So this will cancel. So you get negative n over beta naught plus n over beta naught, and that's 0. So that's part 1, showing the expectation of the score is 0. So now the factorization theorem, hopefully when I do this, it'll make more sense. So again, for any sort of question asked using the factorization theorem, you just get the likelihood and then just figure out which terms only is only a function of the observation. So the likelihood, again, it's going to be, we did it earlier, it's right here. It's the product of the xi's times 1 over beta to the n e to the negative 1 over 2 beta sum of xi squared. So you can split this likelihood into 2 terms. You can see here that this is only a function of the observations. And then here is our sort of g, or a function that involves the parameter beta, and also our test statistic, sorry, and our observation. What am I doing? Let's say this. Yeah. So just by the factorization theorem, sum of xi squared is a sufficient statistic for beta. So another way to think about it is that if you were to sort of take the MLE, so when you're taking the log likelihood and you're taking the derivative, this sort of function of the observations will go to 0, and you're only sort of maximizing this term here. And you need sort of this parameter to do the maximization, or this observation to do the maximization. So that's sort of what it means to be a sufficient statistic. Let me see. I have time. So let's think. I can think of another example. So let's say you had a Poisson distribution. So let's say I had x1, xn following a Poisson lambda distribution. So then recall for the PDF of Poisson, it's e to negative lambda, lambda to the power x over x factorial. So our likelihood would be the product. So just putting terms inside, it'll be e to negative n lambda, lambda to the power xi uh, over the product of xi factorial. So we can think of this as e to negative n lambda, lambda to the power xi times 1 over factorial like that. So this you can immediately, so maybe some of you can see it by now, but this is our sort of function of our observations because it doesn't have lambda anywhere in this expression here, and this part, this is our like sort of function that includes both our observations and our parameter. So here you would say by factorization theorem, sum of xi is a sufficient statistic. Hopefully the factorization theorem and the sufficient statistic makes sense now through these two examples. There may be instances as well, sorry, I should mention this, where you don't have a term of your observation. Like let's say for whatever reason, this is sort of one, then you would just be determine the likelihood that you need, basically. So this would be your sort of function of observation. There might be some distributions where when you take the likelihood, you will not have like a term with only your observations. So keep that in mind. But yeah, this is just generally how to get a sufficient statistic for the Poisson, and then up here how to do it for the, I don't know, this weird distribution here. It looks like some kind of exponential, but yeah. Any questions for this problem? I'll keep this here. Yeah, why not? All right, moving on. Fisher information. So Fisher information is also generally a question you'll probably expect to see on your exam. So you can think of it. What's a good way to think about it? So the formula is pretty simple. The one that I think many people use is not this. Oops, what's my pen? Not this, but rather like they just use this, the negative expectation of the second derivative of the log likelihood, or you can use the negative expectation of the derivative of the score. Oh, oops. Oh, shit, yeah. Because again, taking the second derivative of the log likelihood is just taking the first derivative of the score. And so you can think of Fisher information as just sort of at a parameter, theta naught. It's sort of the expected amount of information about an observation X. Oh, sorry, not this one observation. Sorry, in observation X carries about the true value theta naught. So uh, I would say if you don't really care about what it means, then you don't need to worry about this. You just need to know how to calculate it and sort of when you need to calculate it. So these two are generally the formulas that are used. So this will be helpful when we get to the large sample properties. So for when we have n large enough, the distribution of the MLE will follow a normal distribution with the center at theta naught, and then the variance set to 1 over n of the reciprocal of the Fisher information. So you can think of it as, here's one way to think about it, as sort of n increases, it's sort of decreasing the variance of the MLE. So when your variance is decreasing, your density will get narrower. Oh, and then, so then this is just the standardized version. So you subtract by the mean divided by the square root of the variance or the standard deviation, and you'll get the standard normal distribution. And then this is how you compute a confidence interval. I believe this is in your cheat sheet. I would double check to make sure it is. I feel like it should be. And then the sort of NI theta hat here is the plug-in estimate. So there's two versions. There's the plug-in estimate, which is taking the negative expectation of the second derivative of the log likelihood at the MLE. And then there's the observed Fisher information, which is just taking the negative second derivative. And I think Shams mentioned in his lecture notes that you'll usually be working with a plug-in estimate here. So just using the MLE. And it's what's used here for getting the confidence interval. So, well, I think should be a problem now. Yep. So again, it's just giving 10 random samples from Poisson distribution. And then I gave you guys the mean and also the MLE of lambda. And then it's just asking for a confidence interval for lambda. So I'll give 2 minutes for this problem and then I'll go over it. Yeah. All right. I'll go over this problem now. So this is sort of a large sample practice where, I mean, let's just assume n equals 10 is large enough for this case. So we just asked to calculate the confidence interval for lambda here. So first thing we need to get is the Fisher info. Oh my goodness. Info for a Poisson distribution. So if we have n observations from Poisson lambda, then we need to get, again, to get the Fisher information, we need to get the second derivative of the log likelihood. So we need to get the likelihood, the log likelihood, and then the first derivative and the second derivative. So if you remember, the PDF for Poisson is e to the negative lambda to the power x over x factorial. So then the likelihood is just the product. So this is e to the negative n lambda, lambda to the power xi, or the product of xi factorial. So now we need to take the log likelihood. So, or not the log likelihood, but just the log likelihood. So taking the log likelihood, we'll get negative, negative n lambda plus sum of xi log lambda minus log product xi factorial. So then taking the first derivative with respect to lambda, we'll get negative n plus the sum of xi over lambda, and then this will go to 0. So minus 0. And then now we take the second derivative. So the second derivative, I might have asked you to do this to check the second derivative is less than 0, but you'll get, so this will also be negative n will be 0. This will be negative sum of xi over lambda squared. So then now to get the Fisher information, we need to take the negative expectation of the second derivative of the log likelihood at lambda equal to lambda naught. So this will be negative expectation of negative xi over lambda squared. And then this, so the negatives will cancel. You'll get the sum of the expectation of xi over lambda squared. And this will be n lambda, lambda, this should be lambda naught, sorry. N lambda naught over lambda naught squared. So this will be n over lambda naught. So then remember that for any, for the MLE, it'll follow a normal distribution centered. I'll just write it out here. That way it's easier to see. So remember that theta hat will follow, will go to a normal theta naught and 1 over ni theta naught. So lambda hat will go to normal lambda naught n. So it's okay. So it's the reciprocal. So lambda naught over n. And again, we're using sort of the plug-in Fisher information. And so what that means is we're using the MLE. So then to normal lambda hat over n. So then to get the 95% confidence interval, you would just use the formula that I gave above right here. Where is it? Yeah, this one there. So it'll be 95% CI will be lambda hat plus minus z 0.975 times the square root of lambda hat over n. And if you remember, I gave you guys the MLE here. Lambda hat is equal to x bar. And I also give you the mean of the sample, so it's 2.7. So 2.7 plus minus, this is just 1.96. This is a table value, it'll be on your cheat sheet. And then times the square root of 2.7 divided by 10. So this will be 1.682 to 3.718. Yeah, if you want more practice with this kind of stuff, what you can do is you can just, in R, you can just pick a random distribution. You can do Bernoulli, exponential, I don't know, normal, what else? Gamma if you want to, I don't know. You just pick any of these distributions, generate some values, take the mean of the sample, and then sort of go through and calculate the Fisher information, construct the confidence intervals, and then once you feel comfortable with that, you'll probably be able to execute on the exam. You'll probably be able to do it on the exam with given some arbitrary distribution that he gives. So I think that's all I have for the large sample. Oh, I lied, one more. So the Kramer-Rao lower bound, I'll just quickly go over this. So this might be a question that he might give as well. So the Kramer-Rao bound, it's essentially just putting a bound for any unbiased estimator of theta naught. So what it's saying is that so the variance of any unbiased estimator, let's just call it theta hat of theta, is bounded by the reciprocal of the Fisher information. So basically, you will never be able to get, this is just the lower bound basically, like you'll never be able to get a variance lower than this value. So I would say that's the easiest way to think about it. So again, if you're asked to calculate the Kramer-Rao, all it is just getting Fisher information. So yeah, I'll just give you guys 2 minutes to do this. This is the same distribution or the same distribution or the same density that I gave earlier when you guys did the sufficient statistic and showing the expectation of the score goes to 0. So now this time you're just asked to calculate the Kramer-Rao lower bound. All right, I'll go over this now. I think just for the sake of time, I might break things up and just go over the last couple problems I have. Anyhow, Kramer-Rao lower bound. Okay, uh, so we need to get, so the bound was that it's uh 1 over n I theta naught, where t is an unbiased estimator of theta naught. So we need to get Fisher information for this. So first we need the likelihood. I'll just rederive it again from scratch rather than, I mean, I could easily just scroll up, but that's okay. I think you guys all get the idea of how to do this. And I think by now, many of you guys should be pretty comfortable getting likelihood, log likelihood, all that kind of stuff. So just log. I'll try to hurry this up because this is not the important part. All right, so we're back to the, okay, so we're at the first derivative. So this is what we needed to calculate, I think, last time for this question here. Yep, just the first derivative. So now I'll slow things down and sort of explain things more. So for Fisher information, we need to get the second derivative. So we'll just take the second derivative here. So this will be n over beta squared minus 1 over 4 beta cubed sum of xi squared, I believe. Yeah. So the Fisher information, ni beta naught is the negative expectation of the second derivative of the log livelihood. So it'll be negative n over beta squared, 1 over 4 beta cubed, negative 1 over beta cubed. Oh, did I make a mistake? No, yeah, you're right. This should be that. So when you plug in the negative, okay, my apologies. Thank you for pointing that out. Okay, so going back, it'll be negative n over beta squared plus 1 over beta cubed times the expectation. So it'll be n times, well, I'm just taking the expectation of each of these separately. It'll be n times 2 beta naught. Yeah, just plugging beta naught for all these. Ready? Beta naught, beta naught, beta naught. So then you'll notice that this will cancel out here. It is correctly. Yeah. So this will be n over beta naught squared. Yeah. So then the Kramer-Lau lower bound is equal to 1 over Fisher info, which is just beta 0 squared over n. Yeah, sorry, this was a silly mistake here. All right, so hopefully that's clear. That's Kramer-Rao. Any questions for this? All right, if not, moving on. So now it's about tests, but for the MLE. So we have the wall test, score test, one population likelihood ratio test, and also the two population likelihood ratio test. So yeah, if you get one of these questions on your final, it's usually constructing it, and then after that, he'll probably give you some values, and then you plug in the value and then make a conclusion, similar to the first part. So let's see. Okay, so this was the wall test, but I believe I might have given you, okay, so I gave you the exponential, but I think this is the same one as the one on your fall 2023 exam, which I should have tried a different one. That's okay. I think I'll still go over it, but I'll try to give some. So if you guys want extra practice for constructing wall tests, obviously, just like before, you can try with any other distribution. So again, Poisson is a good one to try. Bernoulli, yeah. So if you want some more practice constructing wall tests, just do the same thing here, but rather than exponential, just change it to either Poisson or Bernoulli here. So for this problem, I'll just go over it quickly, um, just for the sake of time. So the first thing is for the wall test, I'll just write it out here. We need to get the standard error here. So that's the first thing we'll need to calculate usually. So if you remember the standard error, remember we're going to be using the what I mentioned earlier, the large sample property here. So we're just taking basically the square. If we want the standard error, we're taking the square root of this. So it'll be, oh my God, this earlier. So the square root of 1 over ni theta naught. I guess that half. And then what this is, it basically is just going to be, oh, oops, 1 over the negative second derivative. So the not the plug-in Fisher information, but I believe just the where is it? Observed Fisher information. So we're gonna have to rederive the likelihood again from scratch. So uh, I'll try to do this quickly, just for the sake of time, because I think many of you guys are probably already comfortable by getting the likelihood. So exponential distribution, it's 1 over theta e to negative 1 over theta x, where x is greater than 0, theta is greater than 0. So I'll just speed through this real quickly. Let me know if I make a mistake. So, okay. Okay. First off, I think I should be getting the MLE since I don't have that either. Yeah, I didn't give the MLE. Okay, so I'll get the MLE first. So again, getting MLE. This is pretty standard, setting the score to 0. So okay, now we need the second derivative. So taking the second derivative of this here, this will be n over theta squared minus, hopefully no mistake this time, 2 sum xi over theta cubed. Yeah. So then, now that we got that, we can get our standard error. So standard error, so negative L double prime theta, and then sum of xi is just nx bar, because yeah, over x bar cubed. So this is negative n over x bar squared plus 2n over x bar squared. So this is n over x bar squared. And then now we go back to the wall test. So theta hat, oh, x bar, I'll just write theta hat, minus theta naught over the square root x bar squared over n goes to a standard normal over rather x bar minus theta naught. And then your rejection region, since this is just a standard normal, it's just the standard z alpha by 2, z 1 minus alpha by 2. And then, yeah, standard rejection region. So any questions about constructing wall tests? I think this was the same one as the practice exam that he gave. So yeah, I apologize for not changing it before the seminar. But if you want more practice, again, try it with a Poisson, try it with a Bernoulli. Um, yeah, that would be my advice if you want more practice with the wall test. Okay, almost done. Just two more problems. Oh, sorry, I lied. A couple more than that. So now we're just using values. We're just using the wall test that we constructed. Now we're just plugging values in into this here, and also uh, making a conclusion based on the rejection region. So we have 10 values drawn from an exponential distribution with some unknown theta. And we want to test if theta equal to 2 versus theta not equal to 2, at alpha equal to 0.05 using the wall test. So x bar, so we have the sum here. So x bar is just 16.51 over 10, 1.651. And using the test statistic that we calculated earlier, I'll just put it back down here. So x bar minus theta naught over the square root of x bar squared over n is equals to normal, standard normal. And then, yeah, again, you're just plugging in values, put it into your calculator, do what you need to do. Minus 2 over square root 1.651 squared over 10. And this is, I believe, negative 0.668 rejection region. So negative infinity to z 0.025 union z 0.975 to infinity. Again, negative 1.96. I think some of you might have seen this value many times already. So there's the rejection region. So since the test statistic doesn't fall into our rejection region, we fail to reject the null hypothesis at alpha equal to 0.05. So there we go. That was just using our wall test. Moving on. So constructing a likelihood ratio test. So now we have two samples, x1 to xn from Poisson lambda x, y1 to ym from a Poisson lambda y, and you know that they're independent of each other. Construct a likelihood ratio test for testing the hypothesis h naught lambda x equal to lambda y versus the alternative lambda x not equal to lambda y. Give the test statistic, rejection region, and the distribution. I think we have time. I'll give you guys 2 minutes to try this. I think this should be new. I don't think this was on your practice midterm. Or practice final. All right. Maybe not enough time, but I'll go over it now. So this is a two population likelihood ratio test. Sorry, my voice is a little dry. So we need to calculate the likelihood under the null and under the alternative here. And it's just the ratio between those two. That's why they call it the likelihood ratio test. You're just taking the ratio of two likelihoods. Um, so we have two populations, both from Poisson. So remember, the Poisson likelihood is e to the negative lambda, lambda to the power x, lambda to the x over x factorial. So we know that if we have two populations coming from a lambda, from a Poisson distribution, we'll have likelihood with respect to lambda x, lambda y, and it's just the multiplication of those two. So remember, it'll be, if you do the product, it'll be e to the negative n lambda, lambda x to the sum of xi over the product of xi factorial times e to the negative m lambda y. I forgot to write x here, sorry. Lambda y to the power to the sum yj, or make this more clear, I equals 1 to n, j equals 1 to m of yj factorial. And then I think he'll give you the MLE, but or you can just recall that the MLE for Poisson is just x bar, or just that sample average. So lambda hat y will just be y bar. So under the alternative hypothesis, i.e. lambda x is not equal to lambda y, we need to get the likelihood. Lambda hat x, lambda hat y. This is e to the negative n x bar to the sum of xi, all over the product of xi factorial. Again, we're just for lambda x, we're just substituting the MLE here. So then this is e to the negative m y bar, y bar to the power of yj, sum of yj over the product of yj factorial. Let's make clear. Okay. So there's a likelihood under the alternative hypothesis. So under the null, lambda x equals to lambda y. So now we need to calculate sort of the joint MLE. So this is just all the observations combined. So we're just taking the sum of the two combined over n plus m. And then that'll be our equation for lambda hat. So then now our likelihood for lambda was e to the negative n lambda, to the power sum of xi over the product of xi factorial times e to the negative m lambda, to the power yj for the product of yj factorial. Now, if we just plug in the MLE, it'll be e to the negative, we're just combining these two terms here, negative n plus m lambda hat to the power sum of xi plus the sum of yj over the product. Oh, sorry, y index. There. So there's the likelihood under the null hypothesis. So then our test stat is just negative 2 log, negative 2 log the null and then the alternative. So we just plug these two values into here. Oops. Like plugging that equation there, this equation goes there, and that's our test stat. And then I think I might have briefly mentioned above, but this, okay, I didn't. This follows a chi-square distribution. I believe chi-squared 1. I want to double check that. Yeah, I'll double check this. I'll just say it follows the chi-squared 1 for now. It is chi-squared. I'm not sure about the degrees of freedom though. So our rejection region is from the chi-squared. 1 minus alpha, 1 degree of freedom, and to infinity. Let me double check and see if I can find the degree of freedom real quick. Give me 1 second. Okay, it is chi-squared 1. Okay, okay. So technically it should be degrees of freedom equals P minus D. But in this case, D equals 1 and P equals 2. So it's just D chi-squared 1. So uh, I would check week 9 if you're unsure. But I believe P is the number of parameters you need to estimate under the alternative, and D is under the null, if I'm not mistaken. I would probably double check that though, just to make sure. Yeah, we'll go with that for now. Anyways, moving on. Oh, yeah, so this is the test statistic here, and then the rejection region. So okay, any questions for this part here? If not, uh, almost done. There's 2 more problems. So the next part is just plugging in, just given an output and plugging in to our likelihood ratio test that we constructed. So if you remember, let's see, it's 3:30. Yeah, I'll just go over it now. It's just plugging in values. So the test statistic was like this from the previous problem that we did. So you'll notice here, when you take the ratio, these product terms here cancel out with these, what am I doing? With these product terms here. So what you're left with is -2 log e to the negative n plus m lambda x hat. Oh, sorry, this is for the null. My bad. Lambda hat sum of xi plus sum of yj divided by e to the negative mx bar x bar sum of xi e to the negative my bar y bar to the sum of yj. Let me make sure I did this correctly. Yeah, essentially we're just taking this part in the numerator and then just this part in the denominator, because these 2 terms will cancel with each other. And then, oh, I should mention here, lambda hat is sum of xi plus sum of yj over n plus m. So actually, let's go ahead and calculate this now. So sum of xi is here, 6, sum of yj is 12, 6 plus 12 over 2 plus 4, I believe. No, what am I doing? 3 plus 3. 18 over 6, so 3. So then now it's just about plugging in values. So -2 log e, so n and m are 3, n equals 3, n equals 3. So e to the negative, so 3 plus 3 is 6. So -6 times 3, and the hat was 3. 3 to, sum of xi plus sum of yj, so 6 plus 12, so 3 to the 18, over, okay, e to the negative 3 times x bar, which was 2, 2 to the power 6, sum of xi, e to the negative 3 times y bar, which is 4, y bar to the power sum of yj, so 4 to the 12. Yeah. And again, you're just putting it into a calculator. So you'll get, I think, 2.039. And if you remember the rejection region, it's chi-squared is 0.95, alpha equal to 0.05. Yeah. Degrees of freedom equal to 1 to infinity. So this also might have been a standard value as seen quite often. So 3.8414 to infinity. And again, your conclusion will be, since the test stat didn't fall into our rejection region, we reject the null hypothesis at alpha equal to 0.05. Any questions for this part, likelihood ratio test? Again, if you want extra practice constructing likelihood ratio tests, you can obviously try doing it with the one population likelihood ratio test. I think it's a little bit easier to construct than the two population one. And also you can do it again, try it for Bernoulli, try it for exponential, I don't know, gamma, beta. Yeah, any distribution, whatever distribution you like. Yeah, it is a good practice. Uh, okay, almost there. I've been talking nonstop. So last test is goodness of fit test. Um, so this is the formula. So if you have a known PI, you'll use this formula. If you have an unknown PI, I think you'll use this formula. I'm not sure if it'll give you this here or not. I feel like it wouldn't. But I could be wrong. Again, double check the formula sheet just to make sure. So the intuitive sense of like a goodness of fit test, I think it's used mostly in science or like biology. You're just taking, you're just sort of categorizing, uh, and you're taking sort of the expected amount for that's supposed to fall in that category. You're taking sort of what you observe, what you expect, square that difference, and then divide it by the expected count. And then this will convergent distribution to a chi-squared k minus 1, where k is the number of loops you have. So I'll get into the problem here. Suppose I draw 20 values independently from a distribution in R. By grouping the data into 4 equal length intervals, test whether this data comes from a uniform 0-2 distribution. Yeah, just start with this for now. I'll give you guys 2 minutes to try this. This is the last problem I have prepared. Everything else, the Bayesian stuff, and then also the regression was supposed to be covered by Kevin, but I don't think he's coming. So I'll make sure to post the recording that he had as well for that. But yeah, 2 minutes for this. All right, I'll go over this problem now. So goodness of fit. Um, I'm not sure if you'll put a goodness of fit problem on your exam, but again, be prepared for anything. So we'll go over this now. Um, so the null hypothesis for goodness of fit is that if the data comes from a uniform 0-2 distribution, and our alternative is that it does not come. So for the uniform 0-2 distribution, we're asked to sort of partition it into four equal length intervals. So our intervals are going to be, so from the 0-2, we just sort of divide this into four intervals. So it'll be 0 to 0.5, 0.5 to 1, whoops, 1 to 1.5, and then 1.5 to 2. So then obviously if we're just dividing this into four different groups and we have 20 values, our expected count for each group is just 5. So we expect to see 5 in each of these intervals here. So 5 numbers falling into each of these intervals. Um, so uh, so we have our observations here. I'm going to create a table so that way this is easy to see. So we have, create more space here. We have the observed, we have the expected, obviously, and then we have each of the intervals that we made earlier. And then for each of these groups, we expect 5 to fall in each interval. So now we just count. So 0.51 falls in here, 1.81. If I make a mistake, let me know. 0.77. 0.08. Yeah, and it's just pretty annoying, but this is kind of what you have to do. You're just literally looking at where this number, like you're just categorizing it based on which interval it falls in. So 1.32 falls here, 1.56 falls here, 0.24 falls there, 1 falls here, 1.47, 1.19, 1.96, 0.53, 0.5, 1.46. So 4, 5, 7, 4. Okay, so we observed here. Okay, I'll write this. 4, 5, 7, 4. So these are like the number of the numbers that, these are the like observed number that fell into each of these intervals here just by looking at the 20 observations up here. And so now we need to do our test statistic. So our degrees of freedom, again, k minus 1. Well, k is the number of categories. We have 4 categories here, so 4 minus 1 is 3. So then the chi-squared, remember, it's just the sum over all categories of the observed count minus the expected count over the expected count. So at least that's an intuitive way of thinking about it. So 4 minus 5 squared over 5 plus 5 minus 5 squared over 5 plus 7 minus 5 squared over 5 plus 4 minus 5 squared over 5. We're just taking the observed minus the expected divided by the expected. And we're actually, sorry, observed minus expected squared divided by the expected. So it'll be 1/5 plus 0, 4 over 5, 1 over 5. So this is just 6 over 5, so 1.2. And this follows chi-squared. And then we calculated the degrees of freedom here, 3 degrees of freedom with 3 degrees of freedom. And then the rejection region is from the chi-squared. I didn't give alpha. Alpha equals 0.05. I'm very sorry. for all the typos, but yeah, alpha equal to, so 0.95, 3 degrees of freedom to infinity. So this will be, again, table value, 7.814 to infinity. And so we conclude, since okay, sorry, since the test stat doesn't fall into rejection region, we fail to reject the null hypothesis. Any questions on goodness of fit? Sorry, did I calculate this wrong? I might have. I don't want to recount. I think you guys get the process, hopefully. If I count these wrong, I apologize, but you're just seeing like, okay, let's take a value of 0.53. Which of these intervals does it fall in? It falls in the interval between 0.5 to 1. So that's just how you that's how you get the observed count. Um, that's the last problem I have prepared. Oh, and I guess I'll go over how to do this. So if it's from uniform 0 theta, what you have to do is you'll need to take theta to be the max between x1 to x20 between your observation. So basically, you would need to take it the maximum value, which would be 1.96 here. So to 1.96, and then basically you partition uniform 0, 1.9. So you do this, you partition this into 4 intervals, and then you do the same thing that we just did here. So that's how you do it for uniform 0 theta. This is also week 9, if you guys want to take a look. All the tests here, wall tests, score tests, likelihood ratio test, goodness of fit test is all week 9. So any final questions, any final parts you want me to cover, or anything you want me to go back to? I can do that now. If not, that's all my part covered. The rest is just Bayesian, so week 10. And then also the just like a linear regression, which is week, I believe, 11, 12. Yeah, Kevin was supposed to cover these parts. I think he just pre-recorded it. There might have been some confusion, so I'll make sure that that gets uploaded, and then also record. Also, I'll upload the recorded version of this, the one that you guys just sat through as well. So good luck on your exam. Um, hopefully it goes well. Yeah.
Hello, and welcome to the second part of the STAB57 final review seminar for winter 2025. My name is Kevin, and I will be going over Bayesian inference and regression in particular. So to begin, a Bayesian interpretation of probability is that it is subjective and it is a measure of belief given evidence. Typically for the frequentist interpretation, we have our evidence and we have a model that doesn't really change. However, for the Bayesian interpretation, we are given some prior belief and we may update this belief based off of the new evidence that we obtain from sampling some distribution. And we may be able, in this case, we may update our model or its parameters associated with it. To begin with, Bayesian inference follows as a result of the Bayes rule. So if you remember from STAB57, Bayes rule is as follows. Probability of A given B is equal to the probability of B given A, probability of A over probability of B. And we are able to translate this one in terms of samples by letting H be some statistical hypothesis, such as like maybe we have like a null hypothesis as well as an alternative hypothesis. We let I be some sort of prior knowledge or intuition or some prior evidence perhaps, and we let D be the data that we obtain from repeatedly sampling a distribution. Then the probability of H given the intuition and the data is equal to the probability of the data occurring given this hypothesis and intuition times the probability of this hypothesis given the intuition over probability of this data occurring given our prior intuition. So probability of HI in this case will be considered the prior, and the probability of H given I and our new data is the posterior. So this translates quite well from what we know of as the Bayes rule. So the probability of H being equal to some hypothesis H given I, D can be expressed as a random variable of the form pi theta given S, with pi theta without the sample being the prior distribution, and F theta S being what we know of as the likelihood of obtaining the sample given some parameter theta, where theta can be maybe a single parameter like mu or multiple parameters like mu sigma squared. So the probability of data given information is equal to MS is simply a normalization constant to ensure that this pi theta given S is a valid distribution. At the end of the day, if we wanted this excluded, we are able to, as at the end of the day, the proportion of pi theta and F theta S over MS is proportional to just pi theta and F theta S. So this MS value ends up, we are actually allowed to ignore it as long as the final distribution has a total CDF of 1. So given that S is typically pulled from a random sample, naturally we can use the random sample formula, which is F theta S is equal to the product from I is equal to 1 to n of F of xi given theta, where xi is every individual sample. So given a posterior distribution, it is possible to make the same inferences as the ones used in classical statistics. So like the maximum likelihood estimate, as well as establishing like confidence intervals. In this case, they're called credible intervals, as well as, maybe using like maximum a posteriori estimation. For a parameter theta, it is possible to establish a credible interval using the same process as establishing a confidence interval, given our posterior belief of theta. As with confidence intervals, it is in our best interest to make this region as small as possible. Typically for symmetric distributions like the normal distribution, this will be centered about the mean. Maybe for like a different kind of distribution, maybe for like for exponential distribution, it may be starting from 0. The best possible estimate of theta is called the posterior mode. And this is the ideal estimate. So instead of establishing a confidence interval, if we wanted to pick just one answer, we would pick theta hat, which is equal to the mode of theta, which is equal to max of theta. Any continuous distribution, this can be obtained by maximizing the likelihood of pi theta given S using maximum likelihood estimates. Choosing a prior distribution. A family of priors pi lambda, where lambda is in big lambda, which is a sort of a collection of possible priors, for parameter theta is a conjugate prior if for all data S and lambda priors, the posterior distribution is in the same family, i.e. the pi lambda of whatever information given S is still in the same family as pi lambda. So essentially, for example, if we have like a gamma distribution as the prior, if the posterior is also gamma. Perhaps the parameter values itself, as in like theta, may change, but at the end of the day, the underlying distribution is still the same. This is what we call a conjugate prior. Also, sometimes a statistician may not favor any particular prior. For example, if we don't have any evidence regarding whatever we are sampling, we may choose a non-informative prior. Typically, this one would be a uniform distribution over the parameter space. For example, given theta is given we have a finite number of possible, if we have like a finite number of possible parameters, we choose pi theta I to be 1 over n. So every single one of these parameters are equally likely. This really only works if we have a finite number of possible parameters to choose from. We can choose pi theta I to be 1 over n. So pi theta is distributed uniformly. Or for example, we may use something called the Jeffreys prior, which is where the prior is proportional to the square root of the determinant of the information, of the Fisher information. And this way, sort of like the prior, sort of like the posterior will sort of scale with the prior. Sometimes the prior may not even be a proper distribution. This is what we call an improper prior. However, improper priors may still lead to proper posteriors. For example, this occurs when the integral of the prior diverges, i.e. The integral over the prior space of the prior d theta is equal to infinity. So the prior is not a proper probability distribution. This may still lead to a proper posterior distribution, so a finite posterior distribution. Okay, so now we will have a question. Suppose x1, x2, all the way up to xn is IID Poisson, where theta and where lambda is believed to come from a gamma with alpha naught and beta naught as its parameters distribution. Find the posterior distribution of lambda. Find the posterior mean and variance of this lambda. Using a non-informative prior, find the posterior mode. Okay, so if you wish to, you feel free to pause the video and try the question on your own before I give the answer. So, to start with, we are given a that x1 is distributed Poisson, where lambda can be expressed in terms of a gamma distribution. So to start with, let's write out the Poisson distribution. So the Poisson distribution is as follows. So x is equal to e to the negative lambda x over x factorial. So the likelihood of our sample being equal to, let's say we have a sample that we obtain. Now, given our any lambda, given any lambda is, we can just use the definition of likelihood as follows: is equal to the product from 1 to n of, where n is the sample size of e to the negative lambda to the x I over xi factorial, where xi is from the sample, where s is equal to xi, where I is equal to 1, all the way up to n. Now let's go and factor this a little bit. We can bring this one out, right? And since this is lambda to the xi, this product will turn into a sum when it's moved from here to here. So let's do that as well. Equal to e to the negative lambda times lambda to the sum of xi, for xi is from 1 to n, over, I can just keep that over here, let's have it as j is equal to 1 and xj factorial. Okay, so the posterior distribution will be as follows. So pi of lambda given s is proportional to f of theta s, f of lambda, in this case we can lambda s, pi of lambda. So in this case, pi of lambda is gamma, right? So we have the gamma distribution, which is, we have beta naught to alpha naught over gamma of alpha naught times the lambda of alpha naught minus 1 e to the negative beta naught lambda. So this is what we have as the prior distribution, which is just a gamma distribution with alpha naught and beta naught as its parameters. So this one is equal to this one, e to the negative lambda to the sum xi over product xj, or j is equal to 1 to n factorial dot this one over here. So b naught, a naught, gamma alpha naught, lambda a, this one b2 b naught 1. So this one is proportional to short. We have, it's this one is, we can have this, this gamma naught is sort of irrelevant. We can just sort of get rid of terms which we can sort of group together like terms. For example, we have this one and this one are alike, and we have this one and this one are alike. Since it's a multiplication, we can just we can just add them together. These two are constant terms, so we can get rid of that one. And we can also get rid of this one because this one's just a big constant term. So this one is proportional to e to the negative lambda, and then times n. I forgot to do negative. E to the n plus beta naught lambda with the sum of xi plus alpha naught minus 1. And what do you know? This is sort of in the structure of a gamma distribution. We don't have any of the terms here, but that shouldn't really matter because it still follows, like the structure still follows a gamma distribution. Therefore, you can say that pi of theta given s is distributed gamma with parameters, and these are our new alpha naughts and beta naughts. So we have parameters sum of xi from I is equal to 1 all the way up to n plus alpha naught. So this one should be alpha naught over here. So this is alpha naught minus 1, the new alpha naught minus 1. And n plus beta naught. So this one is minus lambda times, this is our new beta naught. So we can say that alpha naught is, the new alpha naught is equal to sum of xi plus our old alpha naught, and the new beta naught is equal to n plus beta naught, our original beta naught. Okay, so second question. Find the posterior mean and variance of lambda. So first, we take the first and second moments of the gamma distribution. We can take the first moment, so mu is equal to alpha over beta, and then we take the second central moment, which is sigma squared, is equal to alpha over beta naught. So the posterior mean is, mu hat, which is equal to alpha naught hat over alpha beta naught hat. Now this one is equal to, we have from before, alpha naught is equal to sum of xi plus alpha naught over our new beta, which is n plus beta naught. And then we take our posterior variance, so posterior variance is sigma square hat is equal to alpha naught hat over beta naught hat squared, which is equal to, same thing as before, sigma xi over alpha naught over n plus beta naught, and then this one be squared. Finally, using a non-informative prior, find the posterior mode. So under a non-informative prior, we do not have any favors toward any particular value of lambda. So the posterior mode instead depends solely on the information obtained by sampling. The posterior mode is the maximum likelihood estimate of lambda. And the MLE of this lambda, so the MLE of lambda is lambda hat is equal to the argmax of L of theta given S, where little l is the log likelihood. So this one is equal to arg max of log e to the negative n lambda to the power of xi over the product of xj factorial j to n. This one is equal to our max of, we can just take out this as entirely. So this one is equal to arg max of a negative lambda. Move this one out, and then plus we can take this one out and then move this one. And move this one into the log. So this one is equal to sigma xi log lambda, and minus, this is the division at the bottom, minus from the sum from I is equal to 1 to n of log xj factorial. So we have a very long formula. However, if we are taking the arg max, we have to, and we also have, so we take the derivative of lambda with respect to this L. We take the derivative of this log likelihood function with respect to lambda, and this is how we maximize this lambda hat. So this one we can get rid of that one entirely, and then this one vanishes, is equal to, let's see, equal to this one. So this one becomes 1 over lambda, because lambda should be strictly greater than or equal to 0, times sigma xi minus, and then we have this n over here, this lambda gets removed, so this one becomes n. So we were left with 1 over lambda sum sigma xi minus n. So setting the derivative to 0, so we set the derivative to 0, so this one, so we have this one is equal to 0. We have 0 is equal to 1 over lambda hat sigma xi minus n. We have that n is equal to 1 over lambda hat sigma xi. And then we have, that means we have lambda hat equal to sigma xi over n. So therefore, we can say that the posterior mode is equal to x bar, which is equal to sigma xi over n. Now we will begin the second part of this recording, which is now we are going to change our focus to regression. So to begin with, what is relevant is correlation. So what is the correlation between two variables? We can express this using, remember the correlation formula, right? We have the covariance, we have a correlation of x and y is equal to the covariance of x, y over the standard deviation, x times the standard deviation of y. This is what we have as the correlation between x and y. To extend this one to samples, instead we take, we don't really know what the expected value of some distribution is, but if we sample it, we can get, so this one is, so we can get, remember that if we sample, we can get that the expected value of x is equal to x bar. We can get that the expected value of x bar is equal to x, the expected value of x. When we sample two different variables, remember that we can get this one and the sample variance, if you can recall, is equal to the sample variance over here. So the correlation coefficient is as follows. Sum of xi minus x bar times yi minus y bar is over the square root of the sum of xi minus x bar square root of yi minus y bar square. And then we have to remember that the bottom part over here will always be greater than the top, or greater than or equal to the top. So the correlation will always be bounded below by -1 and above by 1. So -1 it will be less than or equal to r, which is less than or equal to 1. So the absolute value of r is equal to 1 indicates that the correlation is equal to the standard deviation of x times the covariance is equal to the standard deviation of x times the standard deviation of y, which indicates a perfect correlation. So this one should be similar to knowledge from STAB57, but this time we are applying it to samples. So instead of mean, we use sample means, and instead of variance, we use sample variance. So the goal of regression is we have a set of data points, and for simple linear regression, which is what we are doing in this case, we have our independent variable, in this case is TV, and in this case, our dependent variable is sales, and we want to try to find some sort of line which best fits through all of these data points. So this regression line will obviously take the form of y equals mx plus b, as all lines do in two-dimensional space. We get this regression line is equal to y hat, which is our fitted line, which is our predicted value. This is predicted value, is equal to beta 2x plus beta 1. Okay, so this one is equivalent to the y-intercept, as with y equals mx plus b, and this one over here is the slope of the line. So next, we will define a measurement to see how good this line fits. For example, we have over here, we have a graph. We can take the distance, the minimum distance from this point to this line, or in this case, we are actually taking the vertical distance from this point to this line. And we can take the vertical distance from this line, this point to this line. We can square it. So this one, instead, we square it. So the distances become positive, and then We sum them all together, and this one will give us a estimation to how good or bad our line will fit the data. In this case, the square error is as follows: yi minus y hat I squared, sum them all together, which is equivalently equal to yi minus b1 minus b2 xi squared. Then we sum them all together. This gives us our squared error. So the goal of least squares is to minimize this error. And in minimizing this error, we will maximize our fit of this data. So we can do that obviously by taking the derivative with respect to parameter b1 and b2. So in this case, we take the derivative of this, we get -2 sum times the sum of yi minus b1 minus b2 xi. Obviously, we want to minimize it, so we take it to 0. We know that this function over here is convex. So, maybe we can use like some sort of like gradient descent, or we can just take out the plain old derivative. Either way, we should come up to a single closed form solution of the following form. B1 is equal to yi hat minus b2 x hat. And then b2 will have the following formula, where sum of xi minus x bar, yi minus y bar over sum of xi minus x bar squared, alternatively is equal to sum of xi yi minus nx bar y bar, nx bar times y bar over the sum of xi squared minus nx bar squared. Alternative, you may see me write this one as the sum of squares of x and y over the sum of square of x and x. So the sum of square of x and y is we have x over here and y over here, and the sum of square of x over here and x over here again. So this is how I also may write this value. So in terms of simple linear regression, we assume that yi given x equals xi should be iid normal with beta1 plus beta2 xi and sigma squared. So if we have our answer alternatively, you may also see it as written as yi is equal to beta1 plus beta2 xi plus epsilon, where epsilon is sort of the error. And then this error will be distributed normal, 0, sigma squared. These are equivalent representations, right? Since this one is just this one, but centered at mean 0. To find the best possible line of fit, we can use maximum likelihood estimator method to find the best possible estimators. So the likelihood function is defined as follows: L of beta1, beta2, sigma squared is equal to this, which is equal to all of this, blah, 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 blah. Either way is that from this likelihood function, this likelihood function is, if we were to minimize it, we would get the same following results. So we arrived at the same conclusion. Now, even using like this different, this likelihood representation, we will still arrive at the same closed form solution of B1 is equal to yi bar minus B2 x bar, and B2 is equal to sum of squares of x and y over sum of squares of x and x. Okay, since we have this, we can infer that B1 is distributed normal, where the expected value is beta1, which is the true underlying. So this one over here is what we consider our estimate. So our estimate of beta1 should be distributed normal, where this is the true value, the expected value is the true value of beta1 if the data were to come from a linear relationship. You can say that this one is the true value beta 1, and then times, and then the variance is sigma squared of 1 over n plus x squared, or x bar squared minus the sum square of x and x. So sigma of xi minus x bar squared. That beta 2, or b2 in this case, is distributed normal with beta 2 as the true value, as what we expect, and then we have the variance of sigma square over sigma of x, sum of xi minus x bar squared. So a confidence interval we can use the following values from above, right? We can use the confidence interval methods that you may have learned earlier, where we take the z, where we take the standard normal, and then where this one is equal to the standard error. So this one is equal to standard error, and since we have that B2 is distributed normal of beta 2 and sigma squared over sigma of xi minus x bar squared. We can use this idea that it is distributed normal and just sort of apply it here. So B2, since B2, the expected value of B2 is beta 2, we can just take B2 plus or minus this z of the z score of this standard error over here. What is sigma squared? We don't know what sigma squared is. No, typically we're not provided what sigma squared is. So it is an unknown population parameter, so how can we use it? So instead, we use the estimated value of sigma of yi minus yi hat squared. So this one is essentially equal to the mean square error. Instead, we take 1 over n minus 2 degrees of freedom, since we have yi hat consists of beta 1 consists of, let me see, b1 plus b2 x. So we have two fixed values. So if we fix two of them, we have n minus 2 degrees of freedom. When we sum them all together, we have n, and then we have two fixed values. So n minus 2 degrees of freedom for s squared. So instead, we have a sample variance. So in this case, we use a t distribution instead. So now it will look something like this. B2 is sort of distributed with centered around 0. Since the expected value is beta 2, and then we have plus or minus t with n minus 2 degrees of freedom times square root of s squared over the sum of squares of x and x. So the next part is sort of some particularly applications of regression, especially towards detecting lines of best fit and whether or not they exist. This is called ANOVA, or analysis of variance. So in this case, under analysis of variance, it states that the total sum of squares should be equal to the regression sum of squares plus error sum of squares. Since we can decompose this total sum of squares, yi minus y bar, into yi minus y hat I and y hat I minus y bar squared. So as such, we could decompose this total sum of squares into regression sum of squares and error sum of squares. So regression sum of squares explains the residual, the amount of residual that can be explained through regression, and error sum of square is the amount of residuals that cannot be explained, that can sort of be explained only by factors outside of regression. Typically, this is just random variance, since from before we have that errors should be distributed normal 0 sigma squared. So this error sum of squares should represent this residuals over here. So Total sum of squares is just the sum from yi minus y bar squared. And the regression sum of squares is our best fit of y hat I minus y bar squared. And the error sum of squares is equal to yi minus y hat I squared, which is the residuals. The sum of squares of all the residuals. Next, the coefficient of determination is defined as follows. R squared is equal to RSS over TSS. So R squared is equal to regression sum of squares over the error sum of, over the total sum of squares. And this will explain how much our regression model is explaining. Okay, so higher values indicates that we have a very good model, and the model fits very well with very small error sum of squares in comparison. So when the regression sum of squares, is approximately equal to the total sum of squares, we have that the R squared value is very close to 1. Is very close, is approximately 1. So we have to remember that regression sum of squares is bounded below by 0 and bounded above by 1. This is because regression sum of squares, remember that we squared these errors, so this one will become positive no matter what. And the total sum of squares, this is also squared, so it will always be positive. So this one represents so in simple linear regression, we can have that the correlation is equal to this coefficient of determination. In multiple, and if we have multiple regressions, if we have multiple linear regression, this may refer to like multiple R squared and adjusted R squared. It may be different depending on how many degrees of freedom and how many variables you have. So however, in simple linear regression with only one feature, we have to remember that we only have one explanatory variable, so we have the same degrees of freedom all around the board. Next, we will talk about regression with categorical variables. Let's say we want to apply regression on height with respect to some biological sex, such as male or female. Our independent variable is now xf, where 0, which is an indicator variable, so xi, xf is an indicator for is distributed Bernoulli. So it's 0 if x is male and 1 if x is female. So now our regression formula will look as follows. Y hat I is equal to b1 plus b2 xf, where xf can only take values from 0 to 1. So under our assumption that y given x of x f is equal to x of f is distributed normal with beta 1 plus beta 2 xf and sigma square variance. How can this be interpreted now? It is no longer a slope, but instead we have b1 is equal to mu m, and this is the average of how tall a male would be, and b2 is equal to mu of f minus mu of m, which is the average difference between the male and the female. So in this case, you may also see this with this sort of representation of x1 as a dummy variable. You may also see it being called as so-called one hot encoding. This is especially in context of like machine learning. They typically call it one hot encoding. So for every regression model with categorical variables, there is a base category. The rest of the category is represented using a binary indicator. Once again, this is our so-called one hot encoding. We have that y given b is equal to b, blah, 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 z is equal to z, xz is equal to xz, is distributed beta 1 plus beta 2 xb plus so and so on, plus beta n xz, and sigma squared. And once again, we can still have the same regression representation. However, we have beta 1 is the parameter value of our base category, and beta I is the difference in the value from B beta 1 to category I. So if we want to fit a model, we need n minus 1 different indicator dummy variables. Alternatively, you may see this one being called one-way, this analysis being called one-way ANOVA. Okay, so now on to the question. So given this summary of 5 observations below, so we have n is equal to 5, we have sigma xi is equal to 15, sigma yi is equal to 42, and sigma xi minus x bar squared is equal to 30, sigma y minus y bar squared is equal to 32, and the sum of squares between x and y is 25. Suppose we're trying to fit this following regression model, or alternatively, we have y is equal to beta 1 plus beta 2x plus epsilon, where epsilon is distributed normal 0 sigma squared. So find the maximum likelihood estimate of beta 1 and beta 2 and then interpret the meaning of these two values. Calculate the value of the coefficient of determination, so r squared, and interpret this value as well. Construct a 95% confidence interval for beta 2 and then test our null hypothesis beta 2 is equal to h naught versus the alternative hypothesis for beta 2 being not being 0 for alpha is equal to 0.05, and this is our sort of our p value. What is your complete conclusion? So to begin, we have our best value of B2 is, remember that this one is equal to sigma of xi minus x bar yi minus y bar over sum of squares of xi and x, this one squared. So naturally, given above, we already have these values, right? We have this one, this value above is equal to 25, and this value below is equal to 30. So then we are already given our answer, which is 5 over 6. This one approximately equal to 0.833. So that one wasn't too hard. Then we just take B1, which is, as we remember, this one is equal to y bar minus beta 2 of x bar, and if you remember, y bar is equal to sum of yi over n, and x bar is equal to the sum of xi over n. So this one is equal to, let's see here, the sum of yi is equal to 42, and n is equal to 5 minus, let's just take beta 3 of 0.833. And then we have sum of xi, which is 15. And we have sum, and we have n, which is 5. And this one just becomes 5.9. Then to interpret this, we can say that for every x increase, so for every time x, let's see, for every unit that x increases, y increases by 0.833. Remember, this B2 value represents the slope, and we have the intercept. So, and the y-intercept of this is equal to B1, which is equal to 5.9. So in short, we can represent y hat is as 5.9, which is B1 plus 0.833x. So this is the line that will form as a result of our finding our B2 and B1. Next, we have to calculate the coefficient of determination. So if we remember, the formula for the coefficient of termination is r squared equal to regression sum of squares over total sum of squares. So we remember that the total sum of squares is equal to total sum of squares is equal to yi minus y bar squared. This one, as we've seen above, is equal to 32. And then regression sum of squares, remember, is equal to b2 squared times sum of xi minus x bar. Just double check that one. Yeah. Once I have a bracket around it. Okay. So we have this one, which is equal to 0.833 squared times this one we already have determined out from above as 30. So this one is equal to 20.833. So then r squared is, so that means that r squared is equal to 20.833 over 32, which is equal to 0.65. So in short, this means that the regression model explains 65.1% of the variance, the total variance. And everything else remaining. So the 34.9% remaining. So the remaining 34%, the remaining 35% is left as error of sum of squares. Can be explained by the residuals. So this is considered maybe you can also include that this is considered a good fit. This in the case a strong so the fit is considered to be quite good. Okay, so we're not since we recorded, we went on that one. Okay, so next question is construct a 95% confidence interval for beta 2. So 95% confidence interval for B2. And you have to remember that the expected value of B2 is beta 2. So we're going to say that B2 plus or minus T of 95% confidence interval, 95% confidence interval. We have that this one is equal to 0.975, and then we have n minus 2 degrees freedom times the square root times the square root of the standard error. And the standard error, if we can remember, is equal to the sample variance over the square root of xi minus x bar squared. So then let's take the SI. So S squared, remember, it's equal to the expected, the error sum of squares over n minus 2, which is the degrees of freedom, since we're fixing two values. So this one, this error sum of squares, if we remember by the formula, is equal to total sum of squares minus regression sum of squares over n minus 2. which is equal to, let's check out the total sum of squares. Total sum of square is what? So the regression sum of squares is 20.833 and the total sum of squares is 32. So this one is equal to 32 minus 20.833 over n minus 2, which is equal, for n minus 2 is equal to 5. So 5 minus 2, which is equal 3.722. So then we have, so then this one, we already know what this one is. So this one, so let's say, which is equal to 0.833. This is our estimate of B2 plus or minus the T value for this one is 3.182 with, let's see, 3 degrees of freedom. For 3 degrees of freedom is as follows. So this one is equal to square root of 3.722 over 30. This one is equal to, which will result in the following interval of 0.03 and 1.64. So then we have our confidence interval, our 95% confidence interval is as follows. Next, we have to test if whether or not H naught, beta naught is equal to 0, beta 2 is equal to 0 versus our alternative hypothesis 4, alpha is equal to 0.05. Since this over here and this is identical, we could just use this confidence interval over here. We just use this confidence interval to calculate, to figure out if this hypothesis is rejected or accepted. So in this case, we have beta 2 equals 0. So in this case, our null hypothesis is beta 2 is equal to 0. Since this lies outside of the same confidence, since this lies outside of this confidence region over here, since 0 is less than 0.03, which is the lower end, so we can say that 0 is not inside 0.03 and 1.64, which means that we reject the null hypothesis. So we're in favor of the alternative hypothesis that beta 2 is not equal to 0. So since this, we can say that we reject H naught, and this means that, which also means that there exists some sort of linear relationship. So there exists some linear relationship between X and Y. Okay, and this one should conclude the STAB57 final review seminar. Good luck on your exam, and thank you for listening.